Okay, hello. Hello, everybody. Thanks for coming to my talk. My name is Timur Doumler. I'm going to talk about C++ and safety. And why am I talking about C++ and safety? I'm not actually a safety and security expert in any way or shape or form, and I've never worked in any safety critical industry or anything like that. So why am I doing a talk on safety? So the truth is, I got nerd sniped into it on Twitter by JF Bastian. So I was kind of asking on Twitter, hey, what should I talk about? And JF suggested I should talk about safety and security in C++ because it's a hot topic and because I'm not particularly good at identifying humor and irony and sarcasm and things like that, even if people put smiley faces into their tweets. I said, okay, I'm going to do it because it is a hot topic and I was kind of curious to understand what was actually going on there. And whenever I do this kind of thing of going in and trying to understand what's going on, and it's a hot topic, lots of people have very strongly held opinions which kind of contradict each other, and I don't really know who's right and what's going on, and there's a lot of opinions flying around. I'm trying to focus on the terminology to make sure that we all have the same vocabulary, that we actually know what we're talking about. And so I encountered these kind of three terms that everybody was talking about: safety, security, and correctness. And somehow these seem to be like really, really important properties that people are after when they write C++ or in fact other programming languages. But it seems like different people mean very different things when they talk about things and they use these words. So that I found that quite confusing. So I tried to figure out what do we actually mean when we say safety and security and correctness. And I started digging and I found this definition of safety in a paper by the safety study group that we now have since a couple of years on the C++ committee. They say there that safety is an emergent property of systems, measured statistically and regulated by policy. The prerogative to decide if something is safe is usually reserved by governmental organizations. And so this is talking about safety as kind of a property of a system, as something that's regulated. It's not a very technical definition, in the sense of like when you're talking about C++ and coding. So it felt like it is interesting, but it's not quite what I was after when I wanted to understand what it means for C++. So I kept digging and it turned out that there were like a few other definitions of the word safety that were kind of different. And so I came to the conclusion that using the word safety kind of unqualified is maybe not very useful. And you need to say what you actually mean when you say safety. So this definition comes from a perspective of people who actually work on safety and security critical code, right? And in that context, that definition probably makes a lot of sense. But it's kind of better if you come from like a very specific point of view like this to actually qualify it and say what you mean. So I found a kind of definition on Wikipedia of functional safety, which is something that talks about safety of a system. And so this definition basically says that a system is safe if it basically doesn't do any bad stuff and it doesn't harm anybody, even in the face of bugs and errors and failures. Right? So that's a very helpful definition. But that again talks about safety from a perspective of a whole system. And if you're doing safety and security critical software, that's kind of where you're coming from. You want your system to not do bad things and harm people, right? So there's a lot of regulation in those industries, and if you dig even further, there's all of these ISO standards and other types of standards, and you kind of distinguish kind of safety as not doing bad stuff, even in the face of bugs or errors or failures from either internal causes or external causes. The external causes you can further kind of split into external causes of the environment, like something goes wrong, I don't know, a cosmic ray hits your computer, or misuse by the user. And then misuse can also be then split further into unintentional and intentional. And security, as opposed to safety, deals with this intentional misuse. So the difference between safety and security seems to be that safety is, a system is safe if it doesn't harm people or do other bad things in the face of unintentional bugs or other failures or errors. Whereas security is all about hardening a system against malicious, intelligent attackers that want to exploit weaknesses in your system for some purpose that you probably don't want. And so that is a whole world of safety and security in software, which, again, I'm not the expert in, but there are lots of people who are. One of those people is Andreas Weiss, who's here at the conference and given a talk earlier today. He's also given a talk about at the C++ Now conference about this, and we actually had him on CppCast a few months ago. It was apparently one of our more popular recent episodes. I think that was really cool. If you actually really want to know what what safe and secure, how developing safe and secure software, what that actually involves, you can watch that episode, or you can listen to this talk. It gives you a really good sense of what it's like to develop safe and secure code, as in developing a safe and secure system. But here we are at the C++ conference, and I'm not an expert in designing safe and secure systems, so I'm not going to look at the whole system. I'm going to look at just one slice of the system, which is the programming language, right? So above the programming language is the environment and the user, and below it is the system you run on and the hardware you run on. So I'm not going to look into all of that, but I'm going to zoom in and look at the programming language that we're all using, right? And so we can say that we can introduce this other type of safety, which we qualify as being language safety, right? And this is what I want to talk about. We can say that, and this is a definition that a bunch of people have used, which I think is very, very useful, so I'm going to use the same definition as well. We can consider a program language safe if it has no undefined behavior, right? And we can consider a programming language safe if it doesn't let you write a program that has undefined behavior, right? If it's inexpressible in that programming language to write a program that has undefined behavior, then that programming language is safe. So there's lots of very different types of safety that people are talking about, right? You can divide this further. You can divide it into memory safety, which then, type safety, bound safety, lifetime safety, initialization safety. You're going to talk about all of those in this talk. There's threat safety, arithmetic safety, and something that's not talked about very much, but I do want to mention here is definition safety. So we're going to get into all of those in the rest of the talk. But there's also this other term here, correctness. And so what does correctness mean? Well, if just look it up, this is one definition that I found. Correctness is the state of being free from error. Okay, well, that doesn't help us very much, does it? But again, if you qualify it and you're being a little bit more precise about what you mean, then you find definitions that are a little bit more useful. So there is this definition here which I find very useful, which is functional correctness. A program is functionally correct with respect to a specification, right? So it's a property that is always defined relative to a specification. If for every input it produces output that satisfies that specification, right? So that's a property that is important, but it's very difficult to match because you actually need to have a very precise specification in order to reason about your program being correct. And oftentimes, actually writing the specification with enough precision is actually as hard as implementing the program that kind of is correct with respect to that specification. So it's often kind of almost the same problem, right? So here's an example. This is a brilliant talk actually by Marshall Clough from CppConf from a few years ago, where it's a 1-hour talk which just talks about how to implement this one function, which we now have in a standard library, midpoint, which takes two numbers and gives you a number that's in between. How hard can that be? So here's an implementation. Is that implementation correct? No, why not? Sorry? Overflow. Okay, but what does the specification say? Maybe it says, it does this thing if the numbers overflow, and then this doesn't do that, and so it's incorrect. Or maybe the specification says overflow is undefined behavior, we don't care, and then maybe it is correct, right? So you need to specify it before you can talk about whether the function is correct. And actually, this talk goes into all of the things that can possibly go wrong with this function, and there's a whole hour just about that. It's great. We have this definition. Of course, there's a problem with that property. Not only that it's very hard to write a specification, there's actually a much bigger problem with this. If you want to say that a program produces output that satisfies the specification, we first need to prove that it produces output. That's the halting problem, right? That's actually not decidable. There is no algorithm that can tell you whether that property holds. So we can split this actually into total correctness, which is the property that we just see, which is undecidable because of the halting problem. But then we also can specify something that's called partial correctness, which says we don't know if the function returns an output, but if it does, that's going to be satisfying the specification. So that's slightly easier to prove kind of formally. There's all the stuff like Hoare logic and formal proofs and verifiable languages like Daphne, where you can like do stuff to like prove partial correctness for a program if it's like sufficiently easy to do. For C++ though, it's a lot more complicated. And in general, you won't be able to formally prove that your program is correct unless it's a very simple problem that you're solving. So we need to go about this in some other way. So there was this keynote, which is among the many talks that have been given this year about this topic of safety and security from C++ Now, which was a conference in May this year by J.F. Bastian. And J.F. Bastian said, no functional safety without security, no security without type resource and memory safety. So that's kind of the undefined behavior, free from undefined behavior that we just saw. So we can say that there is this kind of set of language-safe programs, programs that don't have undefined behavior. In a language like Rust, this will be all Rust programs. In a language like C++, it's going to be some subset of C++ programs, the ones that don't have UB. Then within that set, we have another set, which is like secure programs, right? So programs that don't have UB that can be exploited by an intelligent attacker. Within that set, we have an even smaller set of functionally safe programs, which at least within kind of the kind of stack of the C++ world, are not going to do any harm. And then within that, we have this really elusive set of programs that are actually correct, right? And so the interesting thing is that none of the other properties actually imply correctness, right? You can have like no undefined behavior and can be perfectly safe and perfectly secure, but still incorrect. And here's an example. So we're just taking a float number, which is initially 0, and we're just going to add the number 1 to it 100 million times. Okay, so what's the output of that program? Sorry? Yeah, Richard? No, it does output. This is a float. There's no overflow going on or anything like that. So it does output a number, and we really want that number to be 100 million, right? 1 to the 8th. Like this is kind of what you want the output to be, right? But what's the actual output? Some loss of precision. Okay, so the number is actually roughly an order of magnitude lower than what you would expect, right? Because the number in X starts getting bigger and bigger and bigger, and you always add 1 to it. So the number you're adding, so the 2 floating points you're adding start to be very, very different. And if you add a very big floating point number to a very small floating point number, you get accumulating kind of floating point errors. And eventually, it gets so big that it's like an order of magnitude of difference. And that's really bad. Imagine you have like a missile guiding system which calculates the coordinates, like where it needs to fly, and then, there is a bug like this in there. That's probably not going to be good. It's going to land somewhere entirely different from where the people intended it to land, right? And so this is something that is clearly incorrect, but it has nothing to do with the programming language. Like this kind of bug is going to happen in any kind of programming language. Like you need to know that in order to do this properly, you need to account for floating point precision. There is an algorithm that does that. It's called K-Hand summation. You can go and use that. If you're not aware of that, you're going to run into this problem. So there's lots of things like that. Floating point running errors, using the wrong units. Famously, the Mars climate orbiter crashed because of that. Mixing up plus, equals, and equals is also something that no compiler is going to tell you, because how is the compiler going to know what you mean? But it's kind of a thing that you can get wrong. So, there are things you can use to mitigate that. You can do testing. You can do design by contract, which is something we're going to talk about on Wednesday. There's languages like Ada, which kind of help you do this a bit better than C++. But this has nothing to do with undefined behavior. So what we're after here is not this, because this is not a problem that we can solve in general. But what we're after is this property of language safety, like free from undefined behavior. So why are we talking about this now? Well, there have been a lot of things happening in the community over the last year or so, starting with this NSA report from last year, which says, well, exploitable software is frequently based on memory issues. For example, memory buffer overflow and allocating, deallocating memory, stuff like that. Microsoft and Google found that about 70% of their vulnerabilities are due to memory safety issues like that, right? And so it's the fault of C and C++ because they let you do all of these bad things that lead to UB. And so therefore, NSA recommends not using C or C++ and using memory safe languages, right? Like Java or Rust. And so actually we should move the whole community to away from C and C++, and people shouldn't use them anymore. We should use memory safe languages, right? So that obviously created quite a lot of attention in the community. We then had this consumer report, which says something very similar. About 70% of vulnerabilities in browser and kernels are due to memory unsafety, which is inherent to C and C++ and other like non-memory safe languages. So we should stop using them. We should use memory safe languages. And actually, the whole industry itself must shift. There's a resistance to moving off C and C++. We need to overcome it. People should stop using C and C++, right? And so they actually even then promote Rust. And so this is kind of something where you read this and you think, oh, wow, is C++ doomed now? Like, is it all over? Should we all move to Rust? And people start thinking about this. People start talking about this. Even people who have nothing to do with safety and security professionally. And this is kind of backed up. There's lots of talks and literature about this. There's this brilliant talk by Jim Radigan from CppCon 2022, where he actually goes into like how these exploits work. How do people exploit them? And yeah, a lot of these vulnerabilities are indeed due to these things like out of bounds write or use after free, et cetera, et cetera. Then we also have the National Cybersecurity Strategy paper from the White House, which kind of took this whole thing and like blew it up even more and said, lots of things that I'm not going to repeat now. It's you can read it, but like definitely it's vital importance to solve this problem. And it's not just the Americans; it's now also the Europeans. So the EU is working on the Cyber Resilience Act. And everybody wants us to move away from memory unsafe languages. So, one thing that you could ask yourself is, why are governments pushing? It seems that there's kind of this shift from like, safety and security critical software, like medical, automotive, military, which was, regulated already, and kind of critical infrastructure, like the energy grid and aerospace and the kind of stuff that governments really care about, to there's this push from kind of regulating that stuff to like all the software out there. All software written in C and C++ should now move on to memory safe languages. So why are governments and it looks like governments might actually introduce regulation at some point in some form or another. So you can ask yourself, why are they doing this? Well, I don't know, like my guess is as good as yours, but I think that if governments want to secure critical infrastructure, they kind of need to secure everything because that stuff does use lots of software like, I don't know, Boost, for example, which is written by people who are not software and safe and security experts. So they basically want to shift this whole kind of responsibility for, not having undefined behavior basically to the whole software industry. And so, the internet has been full of news like this over the last year or so. There have been lots of talks given on this topic. So at C++ Now, I think about half of the talks, were just about safety and security. There was this keynote by Chandler Carruth. There was a keynote by JF Bastian, which I already mentioned a couple of weeks ago at CppNC. Kind of same thing. We had a keynote by Sean Parent. We had many safety-related talks there. And there's all of this noise, all of this stuff going on in the community. Everybody keeps talking about it. And yes, it is super important. But kind of what I want to try and do is to kind of look at it from a slightly more critical perspective. And, okay, but what problem do we actually have? What is actually going on here? Can I kind of make sense of this as somebody who has like an outside perspective, right? And so I tried looking at this and understanding what people were actually talking about, what was actually going on, and I noticed a few interesting things. So one thing that I noticed is that all of these reports, all of these news articles, all of this material always said C and C++, C/C++, right? None of them differentiates between C and C++ at all. I thought that was really interesting because if you go to the internet and look for, vulnerabilities by language, every source that you find that actually separates C and C++ into different buckets is going to show you something like this. This is a report from White Source, which you can find easily on the internet. And it turns out that C is single-handedly responsible for almost half of all, known security vulnerabilities out there. And C++ is actually way down the list. It's below, Java, for example, and Python, which are actually memory-safe languages. So comparing C and C++ is not really a fair comparison at all. Or like throwing them into the same bucket is not really, it is a fair comparison. What I mean is throwing them into the same bucket is not really fair to C++. That's what I mean. And it's not surprising, I think, right? So in C, we have all of the stuff like row pointers, strings are row char pointers, we have kind of unions, function pointers, row arrays, all of that stuff, pointer arithmetic, right? In C++, we have much better facilities to do kind of the same things, right? We have unique pointer, which, prevents, memory lifetime issues. We have variant instead of union. We have sort of function instead of function pointers. We have containers. We have, instead of these horrible like multi-dimensional row arrays, we have empty span now since C++23. We don't need to do pointer arithmetics like ever in C++, right? We have all of these other tools. They're much, much safer. So why is C++ still thrown into this bucket of memory unsafe languages? Well, these features are safer, but they're not 100% safe, right? Like, there's always a part of the API that can have UB, like the vector operator square bracket. If you put a wrong index in there, you get UB, right? If you have a unique pointer, there is a method called get, which gets you the row pointer. And then you have a row pointer, and it can end up dangling if you write something, if you do something wrong, and then you have UB again, right? So the other problem is that none of this modern C++ stuff is mandatory because we still have to support C, right? So C mostly still compiles to C++. So there's no switch to turn off all of the raw, low-level, unsafe C stuff. And so that's a problem. And let me focus on this a little bit more. So we have this kind of Venn diagram here, and we want to talk about this gray area of programs that don't have UB. And so we can say that language safety is not having UB, and a programming language is safe. It doesn't let you express programs that are not language safe, right? So one thing that I hear people ask a lot, it's actually quite a common question. Now, why is there all of this UB in C++? Can we just not make it ill-formed instead? Can we just not make it into an error so that the compiler just diagnoses that it's UB and don't do that? So can we just not get rid of all of this UB? And yes, theoretically we can. There is Rust, which is a language that doesn't have UB, right, as an example, or Java. But there are trade-offs associated with that, right? So interestingly, we have that like const expert, the const expert subset of C++ doesn't have UB, right? Everything's checked there. You cannot have UB at compile time. But there are trade-offs associated with all of these things. And doing, having a programming language that doesn't have UB comes with all of these trade-offs, right? You, in certain cases, will trade off performance or backwards compatibility, which is very important in C++, or sometimes correctness, or complexity, or expressivity, or portability, or very important for many companies, cost. How much does it cost to do the switch, right? So we have all of these safeties, and it turns out that C++, has none of them because there's unbounded, undefined behavior everywhere, right? We have all of these things. They're part of the language. Where do we go from here? Well, let's look at them in a little bit more detail. I think it's worth just like making sure that we know what these things mean, right? So type safety is the extent to which the programming language prevents type errors. And that is, attempts to perform an operation where you have a pointer or reference to an object, and the pointer or reference tells you it's that type, and in reality, it's some other type. Here, for example, we have a class widget and a class gizmo, and they're not related to each other at all, right? They're not inheriting from each other or anything like that. And so we have a gizmo, and then we just cast it to a widget and call a widget member function on the gizmo. C++ lets you do that, right? Does that compile that code? Well, yeah, depends on your warnings, of course, but like if you switch off warnings, yes, it compiles because this is a C-cast, right? So it says, try a static cast, try a dynamic cast, and if all of this fails, just do a reinterpret cast. So this is a reinterpret cast. Like, don't write C-casts. It's a very good reason to not write C-casts. Okay, so this program compiles, it's gonna run, it's gonna do something. What is it gonna do? So it's undefined behavior, right? But what do you think is actually gonna happen if you compile and run this? Okay, somebody says it's gonna crash. Any other ideas? It will print Gizmo, right? So on Clang, it actually prints Gizmo, right? So it just assumes, well, that member function of that class needs to be there, so I'm going to index into that, but instead there is the other member function of the other class, so that's what's going to end up being called, because that's the code at that address, right? On GCC, something else happens. GCC says, well, you can't cast a gizmo to a widget. That's undefined behavior. I'm going to just remove all code paths that are leading to that line of code because I know it's undefined behavior, so it cannot happen. So it actually optimizes away the whole program. Right. So here's another example. This is the famous inverse square root from Quake 3, which is this like really neat trick how you can like very quickly compute an approximation of inverse square root of a floating point number by casting it to an integer and then doing some magic and then casting it back. I'm sure some of you have seen this. This is a very nice trick from the 90s when computer resources were very scarce. Of course, this is also undefined behavior. This mostly compiles and works for historic reasons because there's lots of code out there that relies on this kind of stuff. But maybe it's going to break in the next compiler update. So we don't want to rely on this stuff. We do have a safe way of doing this. In C++20, we have bitcast, which lets you do exactly the same thing, but in a safe manner, and it's actually just as fast. I have a whole talk just about that from a few years ago. So what do safe languages do? They just don't let you do that, right? They just don't let you express type punning. Like it would be just ill-formed to write anything like that in a language like Rust, right? So in C++, we could do that, but then we would break a lot of existing code that runs in production, like Quake 3, for example. Right? So that's kind of the trade-off here is with backwards compatibility, among others. Bounce safety. So in C++, nothing prevents you from doing something like this, right? You just read an index from the terminal and just use that to index into a vector. And then you can read any memory anywhere, potentially, right? Which might open you up to a vulnerability, or something else might happen, like a crash, right? Slightly different example, right? You loop over the vector, but then the size, is that the actual size of data? Maybe not, right? Maybe this size is some other number, and then you again have this problem. So tools are actually pretty good at detecting this as soon as the compiler the compiler is going to just compile this, but if you have like a static analysis tool or something like this, they're actually really good these days at diagnosing these things. So if you have a case of, everything is known at compile time, this is an example from a screenshot from C-Line, which is obviously my favorite IDE. We have data flow analysis in there, so it's going to tell you, well, this is actually some code that I wrote while I was preparing this talk. There's an endless loop, and I was like, why is this an endless loop? And I was like, okay, so here I'm like using the wrong index here, right? I'm incrementing y instead of x. So then the static analysis tool tells me, well, this is wrong, right? But maybe this is because the numbers are here, they're literal, so the compiler sees them, or the static analysis tool sees them. But if they're dynamic, it doesn't see them. So how do safe languages prevent this from happening? Well, you either have mandatory bounds checking, right? So you just don't have something like operate a square bracket which is unchecked. Or actually, yes, like you have that. And in addition, you actually don't have C++ style iterators, right? So in C++, you have these raw iterators or pointers where you have like 4 things you can do with them. You can take like the first one, like begin, then you can increment them, then you can dereference them, and then you can compare them with the end operator, right? So those are 4 things, and you can do all 4 of them separately, right? And so there's plenty of opportunity for you to mess something up. In safe languages, this is not how it works. This is a talk by Revson. I think it was even the keynote, if I'm not mistaken, at CPPP 2021, where he goes through like the iterator models of safe languages where, this is not how it works. Like they're like basically these operations of incrementing, dereferencing, and comparing to end are kind of all fused together in like one operation, so you can't get it wrong. And actually, there was a talk by Tristan Brindle at CPP on C a few weeks ago where he shows us how to do exactly the same thing in C++. So that's his Flux library. I thought that was really, really elegant, so we decided to have him on CPP Cast. That was actually the last episode that we did talking about that. So you can do it with like a higher level abstraction. You can get to like a safer model, but nothing prevents you from using the raw pointer stuff. And so, but that, doing those safe things has a trade-off, right? So if you have on a language like Rust, for example, you have mandatory bounds checking, which might have a performance overhead, or maybe not. Compilers are actually really good at optimizing them out these days, but maybe not in all cases. And then the other trade-off is that if you have a language where you can't express, the violation of like the bounds violation, then you can't really have, as I said, these like C++ style iterators. So all of the code that's written with C++ style iterators and raw pointers, it's not going to compile anymore in a language like this, right? And you can't even have random access. And you can't even have, raw loops in C++. So if you have like a, programming, you have an algorithm like a sort, which, uses loops quite heavily and random access, and then you want to port that to Rust or some other hypothetical safe, version of C++ that doesn't let you do the unsafe things, then you can't really do that. You have to rewrite your whole algorithm completely from scratch. And the way you write them in Rust is very, very different, right? You don't have random access. You have like these slices and all of that stuff. So it's very, very different. So that one is particularly tricky to like make safe without having to rewrite all of your code, basically. Lifetime safety, well, that is accessing an object either before it was constructed, so it's not even there, or after it's been destroyed. So that's like use after free, right? So a classic one is returning the reference to a stack variable. You can also dereference a null pointer, which is an instant crash, right? There is no object there. There's like a few more subtle things, like you have a vector and then you move, and then you have kind of a reference to an element in that vector, and then you move out of the vector, but then you still have that dangling reference, right? So dangling reference. Or you have a loop which kind of looks okay, but actually turns out this is also UB because you're actually modifying the container while you're looping through it, and so you might work with invalidated operators. So again, static analysis tools are actually quite good at diagnosing that kind of stuff as soon as they can actually see what's going on, right? So another C-line screenshot. Here's an example where you have an iterator to a vector, and then you push back into a vector, and then that might reallocate everything somewhere else, so that invalidates the iterator. So dereferencing that iterator is UB. It doesn't point to the memory anymore. And so in this case, the static analysis tool, the C-lines DFA, can actually diagnose that because it sees what's going on, right? This is kind of local static analysis. There's also a version of this which is global static analysis. Like a pointer is being deleted in a different function, but then the tool still sees that it might be a bad thing if it sees the definition of delete pointer, right? But that's the problem with all of these tools. If they can't see through the code, they can't diagnose the error. And so then either you get UB or you use a language where that is ill-formed, but then you can't do that in C++ because you break everybody's code, right? So that's kind of the basic trade-off here. So in order to fix this lifetime stuff, there's really three ways to guarantee lifetime safety. Fundamentally, it's kind of a bit of an oversimplification, but fundamentally there's like three ways of doing this. You can either track the lifetime of all objects globally, right? This is what a garbage collector does, which obviously has performance trade-offs. Or you can dynamically track all memory accesses, right? This is what address sanitizer does. It tracks every allocation, every deallocation, and if you try to deallocate something that hasn't been allocated, it gives you an error at runtime, which has a massive runtime cost, so you typically can't do this in production. Sometimes you can, sometimes, the safety is so important that you don't really care about the performance trade-offs. So an example is Apple's iBoot, which is kind of the software that boots up your your iOS device. And so for that one, they've actually developed this dialect of C, which is memory safe. So like every pointer is like a fat pointer with like 3 different, there's like more information in this pointer, and it tracks like all allocations and deallocations. And so for them in this particular use case, that was the trade-off. This is actually quite interesting. There was a blog post by somebody who has like reverse engineered how this works. So it's actually quite interesting to read that. So sometimes the trade-off is justified, but if you're doing something which is performance sensitive, maybe it's not. And so the last way to guarantee lifetime safety is basically what Rust and Val and all of these modern languages do, is that you statically enforce restrictions on what you can do with object references, right? So either you have a borrow checker, which is what Rust does, or you have Val's mutable value semantics model, which is a little bit of a subset of that. Or you have a model where you have no mutation at all, like in functional programming languages like Haskell. And the idea is always that you can either have one mutable reference to an object and no other references, or you can have multiple non-mutable references to an object and no other references, right? But you can never have both at the same time. As long as you can statically guarantee this property, like your program does not compile if you try to do something else, then you can guarantee lifetime safety, on the compile level. And this is what Rust does, and this is what all of these other languages do, and it's great. But, we can't really apply this to C++. Like this is kind of the mantra here. Either you have one unique mutable references or multiple immutable references, never both. But it leads, if you've ever written Rust code, it leads to a very different programming style. And just like we saw with the bounce safety stuff, like many algorithms and even data structures become inexpressible. So like, for example, if you have this rule, you can't write a doubly linked list, because a doubly linked list, you have like 2 mutable references to the same node. You can't have that, right? So then in order to implement a doubly linked list, you need to have an escape hatch like Rust's unsafe environment, right? And so there's this paper by a bunch of folks from the Chromium team. They tried to implement a borrow checker in C++, and it's an interesting paper, and they kind of figured out with today's C++, you can't really do it. It just doesn't quite work because the language is not designed, the way the language works, it just doesn't lend itself to a model like this, right? And so why is that? So, we can have a row pointer, for example, to an object, and that's bad, right? So you want to make it safe, so we can use a unique pointer instead. And that's great, because if you use a unique pointer, you always know that the object is within its lifetime. So that's safe, that's good, right? But unique pointer has methods like get or release, right? And if you call release or get, it gives you a row pointer. And then you have the row pointer, and then, if you have a bug, then you might end up with a dangling pointer, so you have all of these safety problems again. So you could say, well, let's just remove these functions, right? Let's just have a unique pointer that doesn't have get and doesn't have release, right? But it doesn't really work because so we need to be able to access an object within a unique pointer, right? Otherwise, the unique pointer is completely useless, right? So you need to have a way of actually calling a member function on the thing that's inside, right? So in Rust, like if you have a box in Rust, like you can do that in a safe way, but in C++, you do that with a dereference operator, right? The arrow operator. What does the arrow operator return? A pointer, right? So you can just call the arrow operator like this, and you have your pointer, right? And in order to prevent this from happening, you need to change how operators and references work in C++, right? And yes, you can do it, but then 99% of existing code is just not going to compile anymore, right? So I'm actually curious because Sean Baxter back in February actually claimed that he, in his Circle project, is successfully implementing a borrow checker for Rust, which kind of goes very much against what the Google people found. I haven't yet seen this. I'm very curious what he's doing there. Like, I believe it when I see it, but hey, it's an interesting project. I'm curious if something comes out of that. But yeah, that's lifetime safety. One more thing that I want to talk about is initialization safety. I actually have a whole talk about this, like 1 hour just about initialization. So I'm not going to talk about this for too long, but basically, yeah, C++ lets you not initialize a variable and then use it, right? So this is a very obvious example, like depending on what use does, if it uses I, if it reads from it without having first written a value into it, you get UB. This is a slightly more subtle example. So you have a struct here, it has a char and a size t, and you do initialize it, right? This is an aggregate, you do aggregate initialization, and then you memcopy it because it's trivially copyable. What's the bug? Yeah, this is a bit more subtle, isn't it? So think about what the memory layout of that class is. So you have a char, then you have a size t, which must be aligned with 8 bytes, right? And then you have 7 padding bytes in between. And you didn't initialize those because aggregate initialization doesn't initialize padding bytes. Value initialization does. So you have uninitialized padding bytes, and then you're reading from them in this memcopy, right? That's undefined behavior. So this is how much of a problem this really is in C++. And so in a safe language, you can just enforce you have to initialize your variables properly, right? Or if you don't, they're going to be implicitly initialized to some default value, like just zero it out, right? So if you have a greenfield, like new language, you can do it. Can we do this in C++? Well, technically we can, but there's all those trade-offs here, right? So we could just say, well, you have to initialize your variable, otherwise it's ill-formed. We can do it. We can change the language specification to do that, but then it's going to break all the code out there, right? So nobody's going to use C++ anymore if their code no longer compiles. This is kind of a solved problem if you do need this, because if you have any reasonable static analysis tool, it's going to be able to tell you, hey, you didn't initialize your variable. And so if you do need that, you can always switch it on, but you can't just demand that this is how the language works from now on. So here's a paper by J.F. Bastian to try and do something slightly different that's not going to break the world. By the way, there's lots of kind of committee papers here. They all have this paper number. So if you go to a browser and type w21.link/paper number, you're going to get to that paper and you can read it. This is how this works for every standards committee paper, right? So this is where you can look at all of that stuff. So JF's proposal says, well, if we have a variable of automatic storage duration like this I, let's just implicitly initialize it to 0. And so there's a bunch of trade-offs with that. There's a trade-off between, so this is going to be safe, right? You're not going to have UB anymore. Everything's zeroed out. That's great. But there's a bunch of trade-offs. There's a correctness trade-off. 0 might not actually be the correct value. If it's wrong to do that, you can have a tool that tells you initialize it. If it's no longer wrong to do that, you might not be aware that you're getting 0. 0 might be the wrong thing. For example, on Unix, I believe 0, the user ID 0 means root, right? That's probably not the default value that you wanted. There is a trade-off with expressivity. Like, what did you mean? Did you mean to not initialize the variable, or did you mean to initialize it to 0? Like, the difference becomes inexpressible now. And there's a performance overhead. Like with a single variable, like JF proved that it doesn't really matter performance-wise, but if you have an array of 1 million ints and you need to initialize all of them to 0, and there's no way to not do that, high-performance computing people are not going to use C++ anymore. So you need an escape hatch, right? So you need some kind of uninitialized attribute that says, no, I really, really wanted to do this unsafe thing. But then that increases the complexity of the language, right? So that's another trade-off. So there's always these trade-offs. But this particular problem, there's now 3 papers, the last one actually compares all the different trade-offs of the different things that we might be standardizing in C++26. It's a matter of ongoing debate. It's, I think, too early to say who's gonna win or what we're gonna end up doing. Hopefully we're gonna solve this problem one way or another, but let's see. Then there's, of course, thread safety. Like C++ doesn't prevent you from doing things like incrementing the same variable twice from 2 different threads, which is a data race, right? Which compiler can just say, this is never going to happen, and optimize your program based on that assumption, like we saw with the Gizmo and the widget. You get very weird results that way. And you can also get all kinds of other effects, like torn values and crashes, and maybe not with int, but with other things. Like race conditions are really bad, right? Here's another kind of more typical case that I've seen a lot in production in audio code. You have one thread, which is the GUI thread, where you'd turn some kind of gain knob, right? So it reacts to you physically turning the knob with your mouse. and sets the gain, and then the process is in another thread, and the process thread, it reads that gain and does some audio processing with it, and it's just a float, right? So again, data race. Some people think if they make it volatile, it fixes that. No, it doesn't. I mean, it gets rid of some of the optimizations that the compiler is otherwise, allowed to do, but it's still undefined behavior, so you kind of have to make it atomic, or if it doesn't fit into an atomic without being lock-free, you have to do lock-free programming, or you have to use a mutex or whatever. So safe languages handle this in very different ways. In the Java model, basically everything is sequentially consistent, atomic access, and so you don't have data races. You can have weird stuff. You can, read, if you read and write values from the same thread, from different threads simultaneously, you get torn values, very inconsistent values. But it's kind of bounded UB, right? It's not going to bring down your Java VM. You're just going to have weird, wrong values. That's kind of the worst thing that can happen. So it's kind of not really safe in that sense, but at least it's not unbounded UB in the sense that C++ does. Well, in the Rust model, you have the borrow checker, which applies in the same way to threads, so it just doesn't let you have one mutable reference to the same variable from one thread and one mutable reference to the same variable from another thread. It doesn't let you do that, right? Because of the way the borrow checker is designed. You're going to get a hard compiler error. So we can't do this in C++. What can we do? Well, there's a bunch of tools, right? There's threadsan, which is good, but it only finds the races that actually happen when you run it. It can't find all the races. And it masks races because it actually introduces new synchronization points. So it's good, but doesn't find everything. There's cases, anything that involves some kind of side channel, right? Where one thread creates an object and placement news into a buffer, and then another thread reads from that buffer. threadsan probably is not going to be able to diagnose that. There's a bunch of other tools. There was this Jinx debugger, which actually had this idea of deterministically interleaving all the threads and all the combinations and then finding your bugs this way. I think nowadays, it's been discontinued. Nowadays there are other, I think probably more clever tools, but I don't think any of them can comprehensively diagnose race conditions. So the only way we know how to do this reliably is with annotations. I think Clang has a thing that you can annotate your code with thread annotations, but the question is, does that scale? Some people say it doesn't really scale. So we don't really have a solution for this. Then there's arithmetic safety, right? Signed integer overflow is UB. Here's one of my favorite examples. You multiply this number with, I don't know, what is that? 1 billion. But the compiler knows that signed integer overflow cannot happen, right? So because that would be UB. There cannot be ever UB. You can optimize based on the assumption that UB is not going to happen. So it knows that I times this number is never going to be in max, which is 2 billion something. So it can actually move this multiplication out of the loop and do it like this. And this is an equivalent transformation. And then it sees, well, this number is bigger than in max. So this is always true. So then you get an infinite loop. Right? So this is the kind of stuff that can happen with UB. So in safe languages, you don't get this, right? In Rust, for example, you get a panic in debug, and in release, it kind of wraps around the way it does for unsigned. In Java, I think there's a mode where you can throw an exception. Or again, you can fall back to some kind of defined behavior, right? But that has, again, trade-offs, right? Unsaid integer overflow is not UB. So that's also interesting, right? So most of the time when this happens, it's a bug. There's lots of algorithms that break if the unsigned integers overflow. But sometimes it's not a bug, right? I've seen use cases in graphics and in crypto as well, where people actually exploit the behavior of unsigned integer overflow, the wraparound behavior. And so, we can't reason about whether it's intentional or whether it's a bug. And then there's the definition safety, which is the odd one that people don't talk about so much. But we don't have that in C++ either, right? We have ODR violations. We have this thing, ill-formed, no diagnostic required, where if you have two different definitions of the same class and two different translation units, you link them together, you get really weird, hard to diagnose bugs. And in safe languages, you don't have that problem because the way the building and linking works works differently, right? So where are we with all of this stuff? C++ has a lot of UB, right? And we saw that some of it can be avoided by good engineering practices, or some of it can be diagnosed at compile time, and we have very good static analysis tools But they need to be able to see through your code. They need to know everything at compile time. Sometimes they don't, right? Because it's something that's a dynamic property, right? Some stuff you can catch at runtime with sanitizers. Some things can be avoided by using higher level abstractions, right? Like raw mutexes, are dangerous. You can have deadlocks, you can have other things, but you can wrap them in boost synchronized value or lib-guarded, which kind of doesn't let you access things in an unsafe way because it adds like a higher level abstraction to it. And some of the stuff we can fix by evolving the C++ standard and making certain things not UB anymore. But some things we can't fix this way because it would break too much code or would have too bad performance implications. So my thesis, number one from this talk, is that we cannot completely eliminate undefined behavior from C++. We just can't. It's not possible to do that. Or if you try, then the language we end up with is going to be so different from C++ that it's not going to be C++ anymore. Now, security experts are saying again and again and again and again that we have not addressed safety until we have eliminated all UB. And from that, we can derive a corollary. C++ will never be a safe language. So I think we just need to accept that. C++ will never be a language that is completely memory safe the way Rust is. And that's fine, because that's not what it's there for. Does it even matter? The good news is, a lot of this UB, we have very good ways of handling this, right? We have, if you know what you're doing, you can write tests. You can make sure that your tests cover your code. You can use fuzzing. There's a very good coding guidelines, core guidelines, MISRA. This is the one specifically for safety critical code. You can have mandatory code reviews. You can have static analysis tools, which are not going to catch all of it, but they're going to catch a lot, and sanitizers and stuff like this. And a hallway discussion at a conference, like this one, a few months ago, somebody very, very senior at a company that does safety critical code, very big company that does safety critical code, says this works for us. You don't have to move away from C++. The same person went on to say, well, companies get hacked because of vulnerabilities in network libraries, for example. And those libraries are written by people that don't apply these good engineering practices, and that is the actual problem. So I thought that was very interesting. Then you hear the other side of the story, which is security experts. Security experts are saying, well, this is not watertight, and they are right, it's not, right? Tests are not written with exploits in mind. They're written maybe with safety in mind, but not with security in mind, typically, right? They're not targeting a smart attacker. Fuzzing is great, but we are seeing, security experts, that it has not reduced the number of exploits. Coding guidelines are good, but they're not a comprehensive solution because you can't have a static analysis tool that, proves all cases, because that's just impossible if you have, things that depend on runtime properties. And many bugs are not caught by these tools, or if they are caught, then you write code to fix that, right? And every code that you write has bugs, and therefore whenever you fix something that the static analysis tool flagged, you're potentially introducing more bugs. Sanitizers are great, but they're not deployed in production because of the massive performance cost. There is no standard set of tools, like which tools are we supposed to use? That's not standardized. And threat safety data races are not caught by any of this. So yes, they're right. So, there is no such thing as safe code. Even outside of C++, right? There's kind of a bit of an illusion. Safe languages have to code into unsafe ones. There was a delicious thread somewhere where Rust people tried to figure out how to read an environment variable, which is a C function that is inherently, unsafe. So you have to kind of add a higher level abstraction to make it work. You can't just do that. And the same way as well, you can always write an unsafe system in a safe language, right? You can write a C interpreter in Rust and make it crash. All programming languages have vulnerabilities and exploits, as we've seen, not just C and C++. And so the current debate really isn't about having absolutely safe code. It's just about reducing those 70% that are due to memory safety. And it's not a fact that even if we fix all of these holes, we're actually going to get 70% fewer exploits, because attackers are like a gas, right? They fill all the volume that's available to them. So if you plug that hole, they're going to move on to something else, and you're going to have more exploits in that area. So should we care? Turns out it depends on whom you ask, right? A lot of people right now are saying this is an existential threat to C++. We have to address safety. Some people are saying, well, we don't care. And it kind of depends on what your code is doing, right? if human lives depend on your code not having UB, you're probably going to have a different approach than, oh, glitch, lol, well, whatever. Like, it doesn't matter if the application crashes, right? Nobody's going to die. So it depends on what you're doing. It depends on how many users you have, and it depends on who users are, right? So if you, for example, run a scientific simulation, you're the only user. It crashes, okay, you just run it again, right? If you're in low latency trading, that's another very, very interesting one. So, you care about performance, but if you're in low latency trading, like there are basically no hostile actors, right? No one is trying to exploit UB in your code because everybody's going through the same exchange where they do the trades. Everything's monitored, everything's regulated. If you're trying to do something dodgy, then probably, the following week you'll have heavily armed FBI agents in front of your door. So people are just not doing that, right? So this is something you're not really concerned with in that industry. What you're concerned with is performance, 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 and then probably also correctness. So, we have all of these trade-offs, and they're all important. I want to point out this one in particular because this is very dear to my heart. I've spent a decade of my career working in audio, which is basically real-time and low-latency coding, which is very performance-sensitive, right? And so there are things like, there was a talk where somebody said, well, placement new had this like checks for null pointer, but we know we don't need that check. So that check was actually unacceptably slow for them, that one null pointer check, right? That degraded performance so much for this use case that they said, we can't use C++ like this, right? So it ended up being like actually a defect report on the standard to make it UB, so like go the other way around, right? Another example, std complex, it doesn't allow you to not initialize it. So you have to initialize them to 0. For high performance computing people running scientific simulations, that is unacceptable. So they don't use std complex. They have their own complex, which is going to be very interesting when they standardize std SIMD, and then they learn that they can't use std SIMD with their custom complex class, but let's see. So here's my second thesis. Compromising on performance is at least as much of a threat to C++ as this current safety debate that's been going on for the last year. If we lose those users, it's going to be really, really bad for C++ because performance is the reason people do C++. Now, C++ lets you reason out performance of your code in a way that only C and assembler probably do, but they're not really scalable languages in the same way, right? So performance is the reason people use C++. Safety, in a lot of cases, actually isn't, or at least not this full safety that Rust gives you. And if you need that, Rust is there, use it. So is C++ doomed unless you make it a memory-safe language? And my third thesis is, no, it's not. So I'm actually overrunning by a couple. Is it okay if I overrun by like 2 or 3 minutes? Is that fine? Can somebody, yes? Okay, thank you. So I actually did like a little experiment here. To what extent is undefined behavior in C++ today actually perceived as a problem? And I actually collected some data. So I went on and had this little questionnaire where I said basically, can you answer these 3 questions? Like, basically, how much effort and resources do you spend on mitigating UB in your code? That was question number 1. And it's basically no, some, significant, or a lot. And then the second question was, after you've done all of that, how much UB do you still have left in your code that is a real problem for you? Or how much of a problem is that? And it's none, a little bit, significant, or a lot. And so it turns out that about 2/3 of the people say they spend either no or little effort mitigating UB, and only about 1/3 says that they spend a lot of resources on it. And when we come to negative impact, over 3/4 of people say, well, the impact is either none or some, and only less than 1/4 of people say it's a significant or huge impact of UB that they failed to mitigate, right? So here we have this, I can put this on a 2D graph like this here, and make a heat map. And it turns out that 56% of the people are in this happy quadrant where they don't really spend much effort mitigating UB, and they don't really have UB that is a problem for them. So they're doing great. So here we have 22% of people are in this quadrant where they have to spend quite a lot of effort mitigating UB, but once they do, it's fine. Then we have 11% up here, which they don't spend a lot of effort mitigating UB, and they suffer a lot from it. So maybe these people should change their approach somewhat. These are like 11%. And then we only have 11% here in this really unfortunate quadrant where they say, well, I spend a lot of effort mitigating UB, and I still suffer from it in production. So maybe those people should look at either their engineering practices or maybe switch to Rust if they can afford it or do something else. But the majority of people are actually reasonably happy, and it doesn't depend on the industry. So this is all of them. But then the third question was, what industry do you work in? It turns out, if you plot just the people who work in safety critical industries, you get pretty much the same picture, like automotive, medical, aeronautics, military. Quite a few people from military industry answered this questionnaire, which I was surprised by. And then if you plot non-safety critical only, like games, music, software, education, kind of this kind of stuff where you don't really care too much if it crashes, you know, nobody's gonna die, you still get the same heat map. So there's no difference between industries. I thought that was somewhat surprising, and my conclusion is that today's C++ developers generally do not perceive undefined behavior as a business critical problem. Whether they're right, that's a different question, but they don't perceive it as a problem. So maybe everything's okay, you know? And for some people it is, for others, maybe it's not. If you do need guaranteed memory safety, you write everything in Rust. If you can afford it, but maybe you don't want to, or maybe you can't. So that's also reality. So what do we do then? Well, we have a few alternatives, and I only have a couple slides. I'll let you go in a couple minutes. We have all of these new successor languages that people have been talking about a lot, including at this conference last year. We have CP2, Carbon, Val. Either they're not actually fully memory safe in the way Rust is, or in the case of Val, there is basically no C++ interop. And they're not mature. The only one that's actually mature here is actually Rust. So maybe we should actually invest in C++ Rust interop, and that's where we should be spending our money if we care about safety and security. Then there's all of these formal proofs and provable languages, which works for small, self-contained problems. I was talking to some automotive people. They said that yes, they use formal proofs. They have a model in MATLAB and then Simulink, formal verification, then generate the C code. It works for the code that runs on a tiny little chip that controls your airbag. But as soon as you go to the one that controls your lights, it's already too complicated. It doesn't work, right? Memory checking in hardware, which is something we might get in 10 years or something. I would be very excited. And then we can evolve C++ itself. We can mitigate UB in cases where the trade-offs are right. And we don't sacrifice performance or backwards compatibility. On the committee, we've been doing this all of these years, right? So for C++20, we had bitcast, which makes it safer to do type punning. We had implicit creation of objects where you can just cast a pointer to a buffer to a pointer to X, and it's going to magically create an object of X. So it's no longer UB, right? We fixed, thanks to Nico Yusutis, the range-based for loop thing. You can look that up. That's P2012. We have now start lifetime as. There's a lot of ongoing work here, right? There's, we are trying to remove UB due to uninitialized values. That's like all of that work that I talked about briefly earlier. Due to trivial infinite loops, which are, by the way, also UB. When reading underlying bytes, it turns out you can't even cast an integer to a char and try to read the bytes. That's also UB. So I'm trying to fix that. Actually, it's very, very, very hard in the specification to do that. I don't really know yet how to do it. We have this idea of standardizing lifetime annotations. We have contracts. This is something we're going to be talking about a lot in the keynote on Wednesday. This is a very big, promising topic. Okay, here's the billion-dollar question. Is there a subset or a superset of C++ that is actually safe in the way Rust is? And we don't really know. Some people say yes, some people say no. There is this blog post here which looks at things like similar to what Rust is doing, and maybe we can fit them into C++ somehow. It's an open question, so this is the last slide. This is my conclusion. We can't eliminate all UB from C++. We can gradually remove it where the trade-offs are right, but not everywhere. But I don't think C++ is doomed, and I think it's kind of mostly a PR problem. We have to just communicate clearly what we're doing. We're not trying to build Rust. We're just trying to make the situation better, one little feature at a time. And if you need guaranteed memory safety, use Rust. Thank you very much.